So there's two ways to look at that in terms of the math. Okay, there's two ways you can look at it as error and noise. You can look at it as a good thing, like opportunity. In terms of the math, we can look at the easiest one to understand, and it's usually reported for any exercise-based wearable device. It is called RMSSD, which stands for like root mean squared deviation. Now that formula is essentially, it's a square root of, and I'm going to do the actual version here, which is IBI, and I'll come back to this, 1 IBI 0 over n minus 2, actually. And then there's another one, I'll get in what each of these means, SDNN, which is now how an individual IBI compares to the mean over a length of time. Okay, so if you're not watching this, don't worry, I'm going to start verbally explaining it while I draw a picture of each of the two different situations. So let's start with the first one. RMSSD is comparing sequential beats of your heart. And if you're using the polar tech, remember it is the voltage change that happens that opens the cells of your cardiac, or opens essentially the membrane of your cardiac cells. It allows calcium to come in, that causes the contraction. So it is the nervous input where the result is your heart contracts, that muscle contracts, blood flows out. If you're using something like your iWatch or a Ring, Whoop Band, this thing called a Scosche, other types of watches out there, you are measuring output. You're measuring that blood is now flowing out through your vasculature, and it gets out to wherever you're wearing that device, and it causes a expansion of those vessels. There's more blood that goes through, and that's what these PPG-based devices measure using that. Again, little lights that are on the back. I'm not shining the lights on anybody. Okay, so what ends up happening with the sequential beats is that you would measure the difference between each of them, and then what's on the bottom here, n minus 2, is you average it. The reason it's an n minus 2, don't worry about it specifically the math, but basically it's because since you're doing pairs, you're going to miss one at the end, and you're going to miss one at the beginning, because there is not you're missing one that you need to do that measurement, you're missing one at the end. So you can't quite do the full, whatever you measure, however many beats you take, you actually end up using n minus 2 of them. I'm going to draw here what the beats might look like in one situation, and I'm going to draw them in a second situation. So what I'm drawing in these, in case you're not watching, is I'm drawing as if you are looking at your watch, your band, and you see and plot out what the numbers are, right? You just do what I did. You drew like a little L-shaped graph kind of thing. You said, let's just write down each number in order. Here's what they are. So RMSSD, sequential beats, is, well, actually, let's take a step back. Before we do that, IBI I mentioned. IBI in the strict formula stands for interbeat interval. That is that distance I talked about, the frequency domain idea, that there is a time now between events. So remember, if you're going 60 miles an hour, it's about 1 minute per mile. So you'd expect 1 minute each time. And if it was 1.1 minutes, that 1.1 is different than, say, maybe the one before, which was 1. 1.1 minus 1 is 0.1. And you actually square that, so you don't have to worry about direction averaging out, whether it's less or more. This is actually squared. And this one is squared. So the numerators are squared, so you don't have to worry about going up or down, averaging out to 0. You always want to see how much error there is. Okay, so in the case of this, it'd be this, the distance, essentially not distance, excuse me, the time between these beats, and you'd subtract this one, the second one from the first, the third from the second, the fourth from the third, and then you'd add it all up by, square each one, add it up, divide it by the number that you basically checked. In the SDNN case, you're actually measuring each heartbeat compared to what the average was for however long you choose to measure. 1 minute is pretty common for some devices. 5 minutes is really common in the literature. 10 minutes and even longer numbers were common in the early days. They're a little bit less common now. for anything performance or exercise related, because it just takes too long. And also there's a concern that if you have done some kind of exercise, that you're going to have something that may look like this. This bottom graph shows what looks like these little plotting of the points, the numbers is like slowly going down. It's getting lower and lower. So maybe you started at 70, and by the end of your recording period, you're down to 60, and it's kind of flowing down. What I drew in the top graph is kind of the opposite. It's as if it's ramping up very slowly. So this might be a situation where, here's one possibility, that perhaps you decided that you were going to start thinking and stressing about an upcoming test or upcoming, presentation in your workplace. You start to think about it. You start to think about, all right, I have to do this, and then you start to plan. Your mind starts to go, and then what ends up happening is your brain is using energy. You're becoming maybe a little anxious, but you're becoming stressed a little bit because you're focusing and you're using energy. And stress isn't always bad, but stress does mean something is changing. So then your heart rate goes up a little bit to match that, because your brain needs more oxygen, it needs more nutrients as your heart pumps a little bit faster. Brains are expensive in energy. About 20% of your food goes towards your brain. So we're not very efficient with our brain. That is one thing that our bodies are designed to try and minimize brain energy expenditure, because it's so expensive that you run out of your food in your stores. We'll come back to this at a later time about other types of biosignals, including biofeedback. Okay, so there is two situations that can look very similar, though, if I do the math. So one thing I want to get across right here is that the math part, the formulas that I drew on here, are what you get to see. And lots of times you only get sent this top one, RMSSD, which is looking at comparing sequential beats. There are a few devices. I'm pretty sure the Oura Ring doesn't say it specifically from the literature I saw from them, but I bet they do somewhere. They, I think, use this SDNN number more frequently. That's the average when they do your sleep analysis. And the reason why they might use that one is because over longer periods of time, this would show if something has really started to change. Okay, and whereas beat-to-beat measurements might not be that different if you look at a very short period of time. It's like, you're sleeping. You're pretty much always around, let's say, 55. But over time, when you go through, say, REM sleep, or when you go through beta wave sleep, you might have a little bit of change in the variation in your heart, and that might show up more easily when you look at what's called this SDNN. So that's comparing any given beat to what the average was over, let's say, a minute during beta sleep, and then they'll report that number. And then they'll look over a minute during REM sleep, and they'll report that number, and those numbers can look different. Either way, though, you get a number. In the time domain, you get a time. So the number lots of times you'll see, let's try a different color, is you'll get something like 48 milliseconds reported on your, let's call that, say, 48 milliseconds. And this one, oh, look at that. Actually, surprise, it shows up as 48 milliseconds too. So whether it's going up, your heart rate's going up slowly, or whether it's going down slowly, you might get the same number. So that's a yellow flag right there.